Welcome to our video about the 8 best machine learning algorithms. Machine learning is a rapidly growing field that has the potential to revolutionize industries from healthcare to finance to entertainment. But with so many different algorithms to choose from, it can be difficult to know which one is right for your project. In this video, we'll be exploring the top 8 machine learning algorithms on the market, comparing their strengths and weaknesses, and providing examples of how they're used in the real world. So whether you're a data scientist, software engineer, or just someone interested in learning more about machine learning, stick around and let's dive in. 1. Transformers. The work outlined a novel architecture that promoted attention mechanisms from piping an encoder/decoder and recurrent network models to a central transformational technology in their own right. The approach was dubbed Transformer, and has since become a revolutionary methodology in natural language processing, NLP, powering, amongst many other examples, the autoregressive language model and AI poster child. Transformers elegantly solve the problem of sequence transduction, also called transformation, which is occupied with the processing of input sequences into output sequences. In contrast to the recurrent neural networks, RNNs, that had begun to dominate ML research in the CUDA era, transformer architecture could also be easily parallelized, opening the way to productively address a far larger corpus of data than RNNs. 2. Generative Adversarial Networks, GANs. Though transformers have gained extraordinary media coverage through the release and adoption of GPT-3, the Generative Adversarial Network, GAN, has become a recognizable brand in its own right, and may eventually join deepfake as a verb. First proposed in 2014 and primarily used for image synthesis, a generative adversarial network architecture is composed of a generator and a discriminator. The generator cycles through thousands of images in a dataset, iteratively attempting to reconstruct them. For each attempt, the discriminator grades the generator's work, and sends the generator back to do better, but without any insight into the way that the previous reconstruction erred. 3. Random forest. Random forest is an ensemble learning method that averages the result from an array of decision trees to establish an overall prediction for the outcome. If you've researched it even as little as watching the Back to the Future trilogy, a decision tree itself is fairly easy to conceptualize. A number of paths lie before you, and each path branches out to a new outcome which in turn contains further possible paths. In reinforcement learning, you might retreat from a path and start again from an earlier stance, whereas decision trees commit to their journeys. Thus the random forest algorithm is essentially spread betting for decisions. The algorithm is called random because it makes ad hoc selections and observations in order to understand the median sum of the results from the decision tree array. Since it takes into account a multiplicity of factors, a random forest approach can be more difficult to convert into meaningful graphs than a decision tree, but is likely to be notably more productive. Decision trees are subject to overfitting, where the results obtained are data-specific and not likely to generalize. Random forest's arbitrary selection of data points combats this tendency, drilling through to meaningful and useful representative trends in the data. 4. Naive Bayes. Coupled with density estimation, C4, above, a naive Bayes classifier is a powerful but relatively lightweight algorithm capable of estimating probabilities based on the calculated features of data. The term naive refers to the assumption in Bayes' theorem that features are unrelated, known as conditional independence. If you adopt this standpoint, walking and talking like a duck aren't enough to establish that we're dealing with a duck, and no obvious assumptions are prematurely adopted. This level of academic and investigative rigor would be overkill where common sense is available, but is a valuable standard when traversing the many ambiguities and potentially unrelated correlations that may exist in a machine learning dataset. In an original Bayesian network, features are subject to scoring functions, including minimal description length and Bayesian scoring, which can impose restrictions on the data in terms of the estimated connections found between the data points, and the direction in which these connections flow. A naive Bayes classifier, conversely, operates by assuming that the features of a given object are independent, subsequently using Bayes' theorem to calculate the probability of a given object, based on its features. 5. K-nearest neighbors, KNN. First proposed by the U.S. Air Force School of Aviation Medicine in 1951, and having to accommodate itself to the state-of-the-art of mid-20th century computing hardware, K-nearest neighbors, KNN, is a lean algorithm that still features prominently across academic papers and private sector machine learning research initiatives. KNN has been called the lazy learner, since it exhaustively scans a dataset in order to evaluate the relationships between data points, rather than requiring the training of a full-fledged machine learning model. Though KNN is architecturally slender, its systematic approach does place a notable demand on read/write operations, and its use in very large datasets can be problematic without adjunct technologies such as principal component analysis, PCA, which can transform complex and high-volume datasets into representative groupings that KNN can traverse with less effort. A recent study evaluated the effectiveness and economy of a number of algorithms tasked to predict whether an employee will leave a company, finding that the septuagenarian KNN remains superior to more modern contenders in terms of accuracy and predictive effectiveness. 6. Markov Decision Process, MDP. A mathematical framework introduced by American mathematician Richard Bellman in 1957, the Markov Decision Process, MDP, is one of the most basic blocks of reinforcement learning architectures. A conceptual algorithm in its own right, it has been adapted into a great number of other algorithms, and recurs frequently in the current crop of AI/ML research. MDP explores a data environment by using its evaluation of its current state, i.e. where it is in the data, to decide which node of the data to explore next. A basic Markov decision process will prioritize near-term advantage over more desirable long-term objectives. For this reason, it is usually embedded into the context of a more comprehensive policy architecture in reinforcement learning, and is often subject to limiting factors such as discounted reward, and other modifying environmental variables that will prevent it from rushing to an immediate goal without consideration of the broader desired outcome. 7. Term frequency inverse document frequency. Term frequency, TF, divides the number of times a word appears in a document by the total number of words in that document. Thus the word seal appearing once in a 1,000-word article has a term frequency of 0.001. By itself, TF is largely useless as an indicator of term importance, due to the fact that meaningless articles, such as a, and, the, and it, predominate. To obtain a meaningful value for a term, inverse document frequency, IDF, calculates the TF of a word across multiple documents in a dataset, assigning low rating to very high frequency stopwords, such as articles. The resulting feature vectors are normalized to whole values, with each word assigned an appropriate weight. Though this approach prevents semantically important words from being lost as outliers, inverting the frequency weight does not automatically mean that a low frequency term is not an outlier, because some things are rare and worthless. 8. Stochastic gradient descent. Stochastic gradient descent, SGD, is an increasingly popular method for optimizing the training of machine learning models. Gradient descent itself is a method of optimizing and subsequently quantifying the improvement that a model is making during training. In this sense, gradient indicates a slope downwards, rather than a color-based gradation. See image below, where the highest point of the hill, on the left, represents the beginning of the training process. At this stage the model has not yet seen the entirety of the data even once, and has not learned enough about relationships between the data to produce effective transformations. This record of progress can be used to inform a learning rate schedule, an automatic process that tells the architecture to become more granular and precise as the early vague details transform into clear relationships and mappings. In effect, gradient loss provides a just-in-time map of where the training should go next, and how it should proceed. The innovation of stochastic gradient descent is that it updates the model's parameters on each training example per iteration, which generally speeds up the journey to convergence. And that concludes our video on the 8 best machine learning algorithms. We hope you found this overview helpful in your exploration of the exciting world of machine learning. From decision trees to neural networks, each algorithm has its own unique strengths and applications. We encourage you to continue your learning journey by exploring each algorithm in more detail and experimenting with them in your own projects. Thank you for watching, and don't forget to subscribe to our channel for more informative videos.